Okay, so I did a recording on this, where I worked this whole problem, and then the recording failed. So instead of reworking it, I'm going to walk you through what I did, which was this problem where the volume is 784 feet cubed, and we're constructing a rectangular box with a square base, and it includes the top. The cost per square foot for the bottom is 20 cents, for the top is 15 cents, and for the sides is quite a bit cheaper at 1.5 cents. So what dimensions will minimize the cost? So the objective function is cost, because that's what we want to minimize. So we have to add up the cost of all the sides separately, because the cost of materials is different for the bottom, the top, and the sides. So for the bottom, it says it's 20 cents per square foot, and the area of the bottom is x squared. So you could do it in cents, or I did it in dollars. So it's 0.2 dollars per square foot times x squared square feet gives you the price of the base. The top also has an area of x squared right here, but its price is 15 cents per square foot, so that's the cost of the top. And then there's four sides, each of area xy right here, and so that's the total area of all four sides is 4xy times the cost is in dollars 0.015. Okay, so then simplifying, I combine these two terms to 0.35x squared. 0.015 times 4 is 0.06. So that's a cost function which has both x's and y's, right? So we can't differentiate it, so now we have to use the constraint. So the constraint in this case is that the volume is 784. Volume of a box is length times height times width, or length times width times height. So x squared y equals 784. I solved that for y to get 784 over x squared, and plugged that in for this y right here. Okay, so then my cost function coming down here becomes 0.35x squared, that's the same, plus 0.06x times, plugging in for y right here is 784 over x squared. Those 1x cancels from the top and the bottom, and then 0.06 times 784 is 47.04. And then I wrote the remaining x in the denominator as x to the minus 1. Then we can go ahead and differentiate, because we're trying to find where cost is at a minimum. So the derivative, you bring your 2 down, is that. Bring the negative 1 down, makes it negative here, x to the negative 2. So then define the critical values, I set that equal to 0, and solve for x. I wrote this x to the minus 2 as x squared in the denominator, and to move this whole term over to the right side. Then multiplied both sides by x squared right here to get 0.7x cubed equals this. Dividing by 0.7 gives you x cubed equals 67.2. So x is the cubed root of that, which is about 4.06559. And then you go find y is 784 over that number squared, which comes out to this. And I did enter it in my MATLAB, and it accepted my answer and everything. So the one thing I didn't do, and let's just go ahead and end this in here, is we should check to make sure it's a minimum and not a max using the second derivative test. So let's do this in a different color here. Okay, so to check, there's the first derivative. You could find the bounds on x, but I think it's probably becoming obvious to you that if x is at its minimum, which would be 0, then the volume or the cost would be 0, so that doesn't make sense. And actually, that's not even possible, because if x was 0, you wouldn't be able to have a volume of 784. So x could get really, really infinitely small, or actually infinitely large. So the interval for x would be open parentheses 0 to infinity. So it's not a closed interval. So we'd have to use the second derivative. The derivative of this would be 0.7. Bring the negative 2 down times this becomes plus 47.04x to the minus 3, which we can write as 0.7 plus 47.04 over x cubed. For all values of x, no matter what you do, if you cube, since x has to be positive, if you cube a positive number, put it in the denominator under 47.04 and add 0.7, it's going to be positive. So that means C is concave up, which means by the second derivative test, we do in fact have a min at these values when x is 4.06. Okay, let me know if you have any more questions on that problem.